Welcome back friends, welcome to this NPTEL online certification course entitled Soil and Water Conservation Engineering. I am Rajendra Singh, Professor Agriculture and Food Engineering Department, IIT Kharagpur. We are in lecture 8 week 2 and the topic today is modifications in universal soil loss equation. This is the part 1 of the lecture. I will continue this lecture also in next class, which will be clear from here, because this is the course content of this week. In lecture 6 we covered universal soil loss equation or the method for finding out the soil loss. In lecture 7, that is previous lecture, we saw how to estimate two major components of USLE or universal soil loss equation, that is rainfall erosivity and soil erodibility. In today's lecture we will see modifications in universal soil loss equation, and this will be part 1 of the lecture, and we will continue with this in next lecture also, where we will see the part 2 of the modifications in universal soil loss equation, and finally in lecture 10, that is last lecture of this week, we will see soil loss measurement. Now coming to modifications, the modified form of universal soil loss equation, the name also is modified universal soil loss equation. So, that is the modified form of universal soil loss equation, that is modified universal soil loss equation. And basically modifications, why modifications were needed? Because USLE, as we saw, is unable to predict sediment yield from a single rain storm event, and we saw when we defined USLE or universal soil loss equation, we say that it gives a long term average estimation of soil loss, and that is why the unit in USLE is for A, that is sediment yield, is metric tons per hectare per year. So, for yearly basis we estimate. So, to overcome this problem that we cannot estimate USLE, using USLE we cannot estimate sediment yield from a single event, Williams in 1975 modified USLE, and the name is given is modified universal soil loss equation or MUSLE. And this modification is based on the fact that runoff is a superior indicator of sediment yield than rainfall, which simply means which is logical, because no runoff will yield no sediment, though there can be rainfall with little or no runoff. That simply means that, because you remember once again we go to the basics, that there are two major components, detachment and transportation. Now, detachment is because of primarily because of raindrop impact, whereas transportation is because of the overland flow or the runoff. So, what it means to say that even if there is a rainfall, there is a rainfall event, there might be detachment, but suppose entire rainfall volume is absorbed by soil, or that is not allowed to flow because of the soil cover on the soil surface, then obviously there will be no runoff. That means there will be no transportation, that means there will be no sediment yield from a given area. So, that is why based on this very fact Williams proposed that runoff is a superior indicator of sediment yield, and that is why he modified USLE by replacing rainfall erosivity index or rainfall erosivity factor by a runoff factor. So, that is the major modification. One of the major components, that is rainfall erosivity index or rainfall erosivity factor R. In previous class we saw how to estimate that is replaced in modified universal soil loss equation by a runoff factor. And this is how the modified form of universal soil loss equation looks, or MUSLE looks, and it is given by this formula, that is A is equal to 11.8 VQ times QP to the power 0.56 KLSCP. So, that means you can see earlier we had RKLSCP, where R was the rainfall erosivity index. So, that is now being replaced by this term 11.8 VQ times QP to the power 0.56, and that is being called as runoff factor instead of the rainfall erosivity factor. Rest of the terminologies you can see are same K, LS, C and P, that is soil erodibility factor, topographic factor, crop management factor or conservation practices factor, they remain the same. And here there are two new terms are coming, VQ, which is the volume of runoff, and QP, which is the peak flow rate or peak rate of runoff. Units are cubic meter and cubic meter per second. And for estimating these two components, that is volume of runoff and peak flow rate, two standard methods are used. So, runoff volume is estimated using the SCS curve number method and peak flow is estimated using the rational method. So, I am sure that these two methods you might have studied in hydrology, but just to take the course forward, we will repeat this here, and if for the benefit of those who have not read, they will be getting it for the first time. So, we start with SCS curve number method, SCN CN method, and it was basically developed by Soil Conservation Service, United States Department of Agriculture in 1969, and that is why the first term of this method, SCS curve number method, SCS comes from the Soil Conservation Service which is USDA organization. But just to let you know that the name Soil Conservation Service now has been changed to Natural Resource Conservation Service, NRCS, but still the method is known as SCS curve number, SCS-CN method only. And this method is based on two fundamental hypotheses. The first one says that runoff starts after an initial abstraction I A has been satisfied, and this abstraction consists of interception, surface storage and infiltration. And basically this hypothesis is very true in nature also, because when we know from our hydrologic cycle knowledge, we know where rainfall occurs, a part of that gets intercepted either by any kinds of abstract object, maybe plant canopy, maybe there are some bushes on the surface or buildings or roads or whatever. So, some interception takes place. Because of the undulating topography on the surface, some part of the water gets stored on the surface, and obviously a part of this gets infiltrated, and then remainder of that basically flows as runoff. So, that means runoff will start only after interception, surface storage and infiltration processes are completed, or the initial abstraction I A, which is the combined term to represent all these abstractions, has been satisfied. That is the first hypothesis. The second hypothesis says that the ratio of actual retention of rainfall to the potential maximum retention S, S is the terminology representing the potential maximum retention, is equal to the ratio of direct runoff to rainfall minus initial abstraction, and mathematically this is represented like this: P minus I A minus V Q. This is initial abstraction, this is initial abstraction, this is surface runoff, and obviously if from the total rainfall, if initial abstraction and the runoff is taken away, then that represents the actual retention, that is the volume of water that is retained in the basin itself. And this is the actual retention, and the its ratio is a division by maximum potential maximum retention, that is the left hand side. On the right hand side, we have a direct runoff, that is the total flow which is taking place, divided by the rainfall minus initial abstraction. So, mathematically this is the second hypothesis, that this ratio of actual retention to maximum retention is equal to the ratio of direct runoff to rainfall minus initial abstraction. And by some mathematical rearrangements, we can also write this equation in this form, that is V q equals to P minus I A square divided by P minus I A plus S, and here the terminologies are: P represents precipitation, I A is initial abstraction, and S is potential maximum retention that we have already seen, and potential maximum retention by drainage basin. and V q is the runoff volume which we want to determine, and that is why SCS curve number method is used, and P is the mean precipitation over the drainage basin. So, these are the terms which are involved in this equation. Now, this quantity I A, which is initial abstraction, that can be expressed as a function of S. That is the hypothesis given by SCS or soil conservation service, and they said that I A is equal to 0.2 S, which simply means that for a given storm 20% of the potential maximum retention is the initial abstraction before runoff begins. So, initial abstraction is 20% of the potential maximum retention. That is the meaning, physical meaning of this expression. And for Indian conditions, several researchers have reported that for Indian conditions the value of I A could be 0.3 S, but still we in India also we use typically we use 0.2 S. And therefore, in our original equation we P minus I A, we replace I A by 0.2 S. So, this is the form of equation we get, that is V q equals to P minus 0.2 S square, and in the denominator we had P minus I A plus S. So, I A is 0.2 S, and that is why we are getting P plus 0.8 S, and if we again make some kind of rearrangement, this is the form of equation we get, which we are calling equation number 1. And as you can see here, this is a one parameter model constraining S only as a parameter. The potential maximum retention is the only parameter in the model, because P is the input for which we want to find out the V q or volume of surface runoff. So, S is the only parameter which needs to be determined, and then this SCR relationship can also be expressed graphically in this form, that is relationship between P, V q, I and F. These are the four terms which are here. So, if you plot precipitation versus time, then this is what we get basically, and here that simply means initial over initial period of time there will be initial abstraction, and then flow will start, but a part of that will be first retained here. So, this is F actually gives the actual retention of a part will be retained, and then whatever remainder is there, that will flow as surface runoff. And the mass curve of the same can be represented here that P versus V q if we plot, then obviously this is the 45-degree line where P is equal to V q. So, from P, I A, F and V q, there are three components. So, obviously the V q, which is the surface runoff volume, that is only this component, and I A is initial abstraction, F is the actual retention of water in the basin. Now, the most important thing is estimating S, that is because it is a single parameter model. So, obviously our focus will be on estimating S, because if you can estimate S properly, then knowing the precipitation we can find out what is the runoff. So, estimation of watershed's potential maximum retention S is the difficult part of applying SCS curve method to watershed, because it is very difficult really to know the potential maximum retention of a given area. So, basically in order to overcome this problem, SCS developed the concept of dimensionless curve number Cn to aid to estimation of S. So, basically that is where the curve number, the second part of the name Cn comes, curve number, which is a dimensionless number which can help us in estimating the potential maximum retention. And then thus they gave a relationship between curve number and S, which is given here. S is equal to 1000 by curve number Cn minus 10. Here the unit of S is in inches. So, if S is to be expressed in inches, then this is the relationship which will tell us what is the, if curve number is known, then using this relationship we can find out the value of S in inches. If we want S to be in millimeters, then this is the form of equation we use. S equals to 25,400 by Cn minus 254. So, this will give us S in millimeters, and then that simply means that we can replace S in terms of curve number in our original equation. This is the equation, and here you remember we are using the previous form, that is S in inches. S in inches we are using here basically. That is the equation just now we saw, that is the form we are using here, and if we replace S in terms of curve number, then this is the form of equation. So, now the entire equation Cn is the only parameter to be determined, that is the curve number is the only parameter. That's why it says it is still a single parameter model, but the parameter now is curve number, and for determining the curve number of an area we need to know the soil characteristics and surface cover characteristics. So, if we know the soil characteristics and surface cover characteristics, then we can find out what is the curve number applicable for a particular area. And for determining curve number, SCS what SCS did, that they classified around 8,500 soil series into 4 hydrological groups, and these groups are designated as A, B, C and D. So, soil hydrological group A, B, C and D. So, all the soils, all the data that was available, all the soils based on their infiltration characteristics, SCR classified them into 4 categories. So, the categories are group A, group B, group C and group D, and of course, it is based on the infiltration characteristics. So, group A is composed of soils considered to have a low runoff potential. So, these soils have a high infiltration rate even when thoroughly wetted. So, that means the infiltration rate range for such soils is 7.62 to 11.43 millimeter per hour. So, if you know that your soil belongs to this the infiltration of the soil of your area in this range. So, knowing this, you can say that my soil belongs to hydrological soil group A. Similarly, group B soils have a moderate infiltration rate when thoroughly wetted, and range is 3.81 to 7.62 millimeter per hour. From group C soils are those that have slow infiltration rate, and the values are 1.27 to 3.81 millimeter per hour, and for group D the value lies, the infiltration rate lies between 0 to 1.27 millimeter per hour, and this has been given by SCS in 1972. So, knowing the infiltration characteristics, we can find out in which soil hydrologic group A, B or C or D our soil belongs to, which soil hydrologic soil group our soil belongs to. And once that is known, then using the cover conditions or cover description and percent imperviousness, we can find out the curve number applicable for a given area or for a given watershed. Now, there is yet another component which is very important, is initial condition and antecedent moisture condition 2. So, the standard runoff table which was given by Soil Conservation Service, that is for AMC 2 conditions, and we will come to what AMC, how AMC conditions are defined. So, from here, as you can see, if we take impervious area which is a parking lot which is 100% impervious, then based on the soil groups, irrespective of soil groups, in fact, in this case the value is 98, which simply means that whatever rainfall occurs, it almost gets translated into runoff. There is no loss infiltration or abstraction in this case, everything is almost getting translated, which is quite obvious because it is impervious area. But if you come to agricultural area and if you take the example of say pasture or grassland or rangeland, then our values vary from 39, 61, 74 to 80. So, 39 to 80 depending upon whether your soil belongs to group A or group D. Higher the value of higher the value of curve number, that means higher the runoff, and you see that group D soils have poor infiltration, that means the more runoff will be generated from there, and that is why the curve number value is high. So, that is from this we can also say that higher the curve number, more will be the runoff generation for a given area. So, knowing the soil hydrological soil group, knowing the cover conditions, that is cover type and what is the hydrologic condition of that, we can use the standard table provided by SCS, that is soil condition service, for finding out the runoff curve number, and these are for AMC2 conditions as already mentioned. Now, as I have already mentioned that there are 3 AMC conditions that are used, that is antecedent moisture conditions 1, 2 and 3. And basically this antecedent moisture condition is defined based on 5-day antecedent rainfall in inches, that is previous 5 days what is the total magnitude of rainfall, that defines in what conditions basically we are. And then SCS has also said the values will differ for dormant season, that means when there is no crop, and then growing season when there is a crop. So, if we take the AMC2, if dormant season, the rainfall has to be between 0.5 to 1.1 inches, and in growing season it has to be between 1.4 to 2.1 inches. So, obviously based on this table we can find out which AMC condition we are working, and if we are working in AMC condition 2, then standard table value which we have obtained from the table, that itself can be utilized, otherwise we have to manipulate our value, and for that also SCS has provided a table for adjustment table. So, these are the curve number values for AMC2 which we read from the table, and based on whether we are working in the AMC1 or AMC3, then we can find out the corresponding values. So, for example, from our table we read the value of curve number is 75. So, if we are working in AMC1, then our value will be 57, and if it is 88, if AMC3 then 88. So, obviously AMC1 lesser rainfall, that means lesser runoff, that means the curve number value will be lower than AMC2 condition, where in AMC3 rainfall value is magnitude is higher, that means more runoff could be expected, and that is why the value is curve number is high as compared to AMC2. So, that means again we see that higher curve number means higher magnitude of runoff. And people have also generated certain kind of nomographs to help estimate the curve number easily. So, here you can see that this is a direct runoff value Q value, and this is the rainfall magnitude in inches, and these are different curve numbers, nomographs for different curve numbers. So, if the total rainfall at a particular place is 5, and if you know that the applicable curve number is 70, then from here roughly we can say that the direct runoff will be 2 inches. So, out of 5 inches of rainfall, if curve number is 70, around 2 inches of runoff can be expected. So, directly if you knowing your rainfall, or if you know the curve number, then you can directly read the expected value of direct runoff from this curve, instead of using, I mean same equation is also used for developing these nomographs. So, after knowing the entire background, let us take a problem and see how to estimate the direct runoff volume using the SCS curve number. So, we have a problem where we have a 71 hectare urban watershed that includes 60 hectares of an area with 80% grass cover, and 11 hectares of industrial development, that is 72% impervious, that is the conditions are given. The soil in the SCS group B, the soil hydrologic group is B. Estimate the total runoff volume for a 24-hour rainfall where P equals to 4 centimeters for AMC3 conditions. So, we have to obtain rainfall is given and AMC condition is also described. So, we need to follow the following steps basically. we have to first find out the area weighted average curve number for AMC 2, which is the baseline condition. Then we have to adjust curve number for soil moisture condition. We are the problem says AMC 3. So, that is why we have to adjust. Then we have to compute the value of S, that is potential maximum retention, and we have to confirm that initial abstraction, which is 0.2 S, is less than the precipitation for runoff to occur. If it is more than that, then obviously precipitation if runoff will not occur, and then we have to finally calculate the surface runoff volume using the SES curve number equation. So, here data given are the total area is 75 hectares, which has two components A1 and A2, 60 hectares open area with 80% grass cover, A2 15 hectares with 72% of impervious industrial area. Soil hydrology group is B, rainfall is 4 centimeters and AMC condition is 3. So, first thing will be to calculate the average curve number for AMC 2 baseline conditions. So, our total area is 75 hectares. So, we have to read curve number table for open area with 80% grass cover. What is the curve number? Area is 60 hectares, 72% impervious terrestrial area, area is 15 hectares. So, if we look at the table, and obviously we have to be in soil group B. So, here for open space good condition, that is grass cover greater than 75, value is 61, and for industrial where impervious is 72, the value is 88. So, for our area A1, the value of curve number is 61 from table, for A2 the value is 88 from table. So, average curve number will be 61 times 60 plus 88 times 15 divided by the total area, that is 75, that is 64.66 or 65. So, the applicable weighted curve number for this area, given area is 65, that we have obtained from the standard curve number tables and also using the procedure. So, obviously, next thing is that we have calculated 65 for AMC 2 condition. So, now we have to obtain the corresponding value for AMC 3, and straight away we can read from table that Cn for AMC 3 is 82, corresponding to AMC 2 Cn equal to 65. So, the applicable curve number for our problem is 82. So, once we know the curve number, we can use this equation relationship. Our precipitation is given in centimeters. So, that means we can use this equation. So, this will give us S value of S, here curve number calculated 82 we are using. So, value of S will be in millimeters, or we can express then in centimeters, that is 5.575 centimeters, and initial abstraction we already know is 0.2 S. So, that will be 1.115 centimeters, which is less than P, P is 4 centimeters. So, obviously, because initial abstraction is less than P, that means there will be runoff, and then finally, we can use this relationship V q equals to P minus I A square divided by P minus I A plus S, and this if we put the value of P, which is 4, I A which is estimated value is 1.115 here, and S which is estimated as 5.575. So, if you put all these values, we get V q equals to 0.98 centimeters. So, that simply means for the given conditions and given area, out of the 4 centimeter of precipitation, we can get the direct surface runoff volume is 0.98 centimeters. That is what we get in this problem. We can also take another problem, SCS curve number, which says that determine the runoff from a watershed of 60 hectares. Data given is depth of rainfall 100 mm, antecedent moisture condition is AMC 1, soil group is C, crop cover is row crop, good condition 40 hectares, woodland good condition 20 hectares. So, obviously, we have to follow the same steps. So, that means we have to find out the area weighted average curve number for baseline condition, which is AMC 2 from the table. The soil group given in this case is C. So, we have to read this column corresponding to hydrological soil group C, and then row crop we have good condition 82, and then here wood grass combination or woodlands 70. These are the values applicable here. So, for 40 hectares our value is 82, for 20 hectares our value is 70. So, 82 times 40 which is here, 70 times 20 which is here, divided by total area will give us curve number which is for AMC 2 condition, that is 78. And now we have to find out the corresponding value for AMC 1, and here in the table we see that we have 75 and 80. So, obviously, for 78 we have to interpolate that value, and that is what we are doing here, that is we are saying that 57 corresponding to 75, and then for next 3 we are interpolating in between 75 and 80, where the value ranges from 57 to 63, and thus we get the value as 60.6, that is corresponding to AMC 2's curve number 78. The curve number for AMC 1 is 60.6, and thus now we can estimate the value of S by putting curve number 60.6 as 165.14 mm. Initial abstraction point 2 S will be 33 mm, which is less than P, and then finally all the estimated value we can put in this equation, because value of P is 100, IA we have estimated as 33, and S we have estimated as 165.14. So, the total runoff generated is surface runoff volume which is generated is 19.34 mm. So, that means for this given area and conditions, out of 100 mm of rainfall 19.34 mm is getting converted into the surface runoff volume. This brings us to end of this lecture. So, where we have seen that we have a modified universal soil loss equation, where rainfall erosive index is replaced by runoff factor, and for estimating runoff factor we have to estimate surface runoff volume, for which SCS curve number technique is used, that we saw in this lecture. In next lecture we will take up the other term, that is QP, that is peak rate of runoff, for which we use Gesnel method. So, we will see how to use Gesnel method to estimate and go further. Thank you very much.